what are the advantages and disadvantages of the different data models? With raster data, the key advantages are, one, it's very simple data structure. This makes it fairly easy to work with and fairly easy to understand. And it lends itself to raster math and overlay analysis being performed very effectively and efficiently. The main downsides are the large data volume. So higher resolution equals much larger file sizes. This isn't as much of a downside as, say, it used to be 10, 20 years ago because of the serious advances in computation, but it can still mean that things tend to take a while when working with raster data. So it takes a long time to upload and download it from the internet, and it can take quite some time to run processing, especially if you're using high resolution data or looking at a very large area. And the other downside, which is more inherent to the data itself and there isn't much of a workaround, is the loss of information during rasterization, right? So the reductions in cell size might lead to the inability to recognize spatial features because things just get generalized or averaged out within the cell. So we can only see that one specific value within a cell. With the vector data model, the advantages are that it's really good for representing discrete spatial features because we can represent the boundaries exactly. They don't have to conform to the specific cell boundaries, and the vector data resolution isn't going to have as much of an impact necessarily on how we represent those features. Another advantage is that because the data structure is very complex, it often leads to smaller file sizes. We can store a lot more information using, relatively speaking, less memory on the computer. The disadvantages are that it's a very complex data structure compared to rasters. So one, it can make things a little more difficult to understand, but it can also make some different tasks more difficult to conduct. So certain types of vector-to-vector overlay operations that rely on intersecting or overlaying multiple layers can actually require a lot more computing power than just stacking over raster images where the domain is all the same. So the math that you do with vector data can be a bit more complex. And again, just to recap, generally speaking, vectors are better for discrete objects, usually represented as one or more distinct objects or regions. Objects can overlap or they can form a continuous coverage, and each object can have many attributes associated with it. Raster data is generally better for continuous phenomena, though it can be used to represent discrete things in some ways. And each layer provides a continuous coverage. So vector can be continuous or discontinuous. Raster is just continuous. It splits whatever domain area that you're looking at into a matrix of pixels or cells. And each cell can only have one value per band, is what it's known as. Band is an individual raster layer. You can stack multiple bands to get multiple pieces of information. So for instance, a visible raster image is usually based on red, green, and blue pixel values. So we measure light in the red section of the visible spectrum, the green section of the visible spectrum, and the blue section of the visible spectrum. Each of those sections of the spectrum is its own band, and so we could display them just as is and show a gradation of intensity of just blue light or green light, or we can stack all three of them and make a RGB image instead. So the logical question to ask is, which is the best data model? And like most things with JS, there isn't one right answer. There is no single data model that's suitable for all types of analysis or all types of data, all types of scenarios. Typically speaking, when working in GIS, you're going to employ both raster and vector data structures so that you can choose the model that's best suited to represent the data you're working with. It might be dictated by where your data comes from. It is possible to convert back and forth between models, but that does result in loss of information and adds error at each step. So if you convert from a raster to a vector, you will simplify the data lose some information. If you go back to raster, you will simplify more and lose more information. It's not like you can just hit the rewind and go back. You add error with each consecutive change you make. And so in lab 2, you're going to get a bit of an introduction into working with raster and vector data, or building on the introduction you got in lab 1. We're going to use census data, which is a vector data type and all of the attributes associated with it, to look at income in Metro Vancouver. And then we're going to use satellite data to look at vegetation coverage. And we're going to overlay the vector data on the raster data to see how they interact, to see how income is related to vegetation or the greenness of certain areas in the city. Do greener areas have people with higher incomes, or less green areas, are there more people with lower income there? And so we're going to work with that data a little bit. We're also going to take raster data and convert it to vector data and see how we can go through that process. And so you get an introduction into a couple different ways that you can work with both raster and vector data and see how they interact and overlay with each other. So typically speaking, most entities could be represented with either a raster or a vector data type, but whether it's practical to do so is very dependent on what you're looking at. So in the example on the left, we are trying to represent hotels. We can represent hotels as points. They are just specific locations. And so we could represent them with the raster view or the vector view in the world. With the vector view, we just represent the coordinates, representing the location of the hotels, and then we can store attributes about the hotel. So, its age, who owns it, things like that, the address. With the raster view of the world, we can represent the points of the hotels as cells in a raster where we say give it a value of 1 if there is a hotel there and a value of 0 if there is no hotel there. But you can see how we have to store a whole bunch of information to just convey the location of 4 hotels, whereas with the points, all we have to store are the 4 pairs of coordinates. Same thing for like ski lifts. With the vector view, we can just represent it using 3 points that connect to form a line, whereas with the raster data view, we have to represent it as cells that either contain or do not contain a ski lift. And so again, we have to store a lot more information to represent one simple feature. So these 2 examples, it's pretty cut and dry where you want to use that you would want to use the vector data model for these, even though you could use the raster data model. Now, say you're trying to represent an area of forest or lake or something. Maybe it's a little less straightforward of a choice. You can represent a lake using points and lines to create an area, a polygon. Or you can represent the lake as a certain area on the raster map. And so this is more dependent on, say, what you're trying to do and how you're trying to analyze it, whether you might want to use vector data or raster data. Are you just trying to represent one lake, or are you trying to represent the land cover of a full area? If you want to represent multiple different land cover types like water, trees, grass, it might be better to use raster data because it's continuous. If you just want to represent the boundaries of water features, maybe it's better to use vector data because you can more accurately represent the boundaries of those water features. Same thing with road networks. They can be represented as lines on a map, or cells that contain or don't contain roads. Again, typically speaking, you want to represent roads with vector rather than raster data. For elevation, you can represent the continuous surface of elevation using the value of the elevation at all the different cells. And usually speaking, the raster data model is better suited for representing something continuous like elevation. But maybe you want to make a contour map, then you could use points to represent lines of continuous, or you could use lines to represent areas of continuous elevation on, say, a topographic contour map. So, most entities can be represented as either raster or vector. If we represent elevation with a raster data model, typically it's referred to as a digital elevation model, or a DEM. And these are, generally speaking, preferable for terrain analysis because of the raster overlay and the math that I was talking about. But topographic contour lines might be easier to read on a map, so they might be preferable for navigation or hiking. Zoning categories could easily be represented as raster data because each building or each area can only have one zoning type, and zoning is continuous across a city, but it might not be the best choice. What if we wanted to store other attributes about each zone aside from just the zoning category? Maybe there's a current zone category and a proposed future zone category, in which case you might want to have different values, or maybe there's subtypes within different zoning categories. Usually vector data would be better for representing this, but you could display it as raster. And again, you can switch between and go from points to surfaces or surfaces to points, and we'll do more work with this later. You've already done a bit of this in lab 1. You can do something called interpolation. So say you have a bunch of point measurements, you can interpolate or estimate all the values between those points. And I'll talk more about the methods that we would use to do that later in the term. Or you can create something like a heat map where you have a whole bunch of points and you convert that to rasters to show the density of the entity within space. And so we did this in lab 1 where we used the kernel density tool to look at the density of cholera cases in London. So that's just a broad introduction into the different data models that we work with in GIS. I'm going to go into these in more detail as we progress through the term. We're going to do a lot more work with raster and vector data. So don't worry if it doesn't make too much sense right now. Just one last thing to follow to round out today's lecture. I'm including a link to a video by Vox on map projections. It's a short video, it's not too long, but one, it'll be good to get a slightly different perspective on map projections to help you kind of build more of a base of understanding of it. And also it's important to keep kind of thinking about it and refreshing your conceptualization of what a map projection is. So I introduced the concept last week and talked quite a bit about it. Just want you to watch another quick video to kind of help round out your understanding of the subject.